So this week we moved into the smaller scale. We've gone through the planetary and mid-latitude scale of weather where we have the fronts and we have the low pressure systems and we've seen where they typically are. Well, now we're going to reduce that scale one more time down to thunderstorms. We add tornadoes as a part of a thunderstorm. So let's see what we can learn about that. All right, what are thunderstorms? We've learned that air, when it becomes unstable, rises and rises faster. It's accelerating upwards. So that's pushing a lot of air up. A thunderstorm forms due to that process of air rising quickly. So they're very small. Look at the scale of these. An average thunderstorm mature 5 to 10 miles across. One thunderstorm now. And it's caused by very fast moving upward air. So, but there are different ways that thunderstorms get classified. We just looked at the single cell. Single cell has a air going up, forms an anvil, reaches its maximum. You have some down and some up, and eventually all of the air begins to go down. The rain ends, cloud dissipates. However, you can have more than one thunderstorms grouped together, which are called multi-cell thunderstorms or multi-cell cluster. And you can also even have these in a line, like along a major cold front. And finally, you have the most intense one, which is the supercell. That is the one where you have the best chance of having a tornado or some kind of severe weather, such as large hail, damaging winds, all kinds of nasty stuff. Single cell, least threat, all the way up to the supercell with the most threat. So thunderstorms move in one direction. So take a thunderstorm that starts out moving eastward or northeastward. However, that thunderstorm, as we've learned, is going to dissipate in the next 20 to 30 minutes. Well, where is a new one developing? Probably to the southeast or south of it. Why is that? Because that's where the more moisture is, usually. In the United States especially, it's always going to be sometime to southeast, southwest. So with that, the new thunderstorms develop there, and they gradually continue to develop on the south side while the line propagates to the northeast. With each cell, the actual line is going to wind up moving to the east. Weird, isn't it? But that's the way it works because of the new development of thunderstorms. Now, here's a map. Where do thunderstorms typically occur? You can see large quantity of thunderstorms in the south, especially southeast, and especially over Florida. But they even occur all the way up in Alaska. And notice, Hawaii gets hardly any. So, in Alaska, in Florida, you wind up with a sea breeze on both sides of the peninsula. So what happens? That air can dip together, rises because it's on a very warm, humid air mass, typically over Florida. So with that, when the air converging begins to lift, there's some instability because of the fact that the the moisture is evaporating and then condensing. When it condenses, it heats, so its rise becomes unstable and develops thunderstorms. So, if that's the most, you would think, oh, well, I got a tropical island out in Hawaii. In the middle of very warm ocean temperatures, it's an island, so yes, we have sea breezes on all sides. We even have mountains there. So why isn't that the same as Florida? Well, the reason is that is literally in the tropics where there is a trade wind inversion. We learned about the trade wind inversion a little bit when we talked about planetary scale. So where the Hawaiian Islands are located, there is that inversion that prevents the air from rising very quickly, very far. So yes, there are showers and all around Hawaii all the time, but they don't rise high enough to make thunder. So what's the definition of a severe thunderstorm? I had to learn this really well working for the Weather Service because I was in charge of issuing these kind of warnings. When you receive a severe thunderstorm warning flash flood warning, a tornado warning. It comes from the National Weather Service. So with that, winds got to be stronger than 58 miles per hour. Hailstones must be equal to or greater than 1 inch, and there may be a tornado, which would be a tornado warning. So you see anything about lightning? I used to get phone calls all the time complaining, wow, I got a severe thunderstorm. And when I asked people what that meant, what was severe about it, it was most often lightning. Lightning is not a criteria for a severe thunderstorm, as strange as that seems. So with that, what causes thunderstorms to become severe? Well, we want the thunderstorms to have a very strong updraft that continues. So what keeps the thunderstorm from getting that? Well, if you don't have wind shear, the thunderstorm is going to have all this air go up, and then it's all going to come back down. When it hits the ground, it's cool, cuts off all that humid air coming into the updraft. We wind up the updraft dying. But if you have vertical wind shear, strong enough, and all that is a change in wind speed or direction, that will allow this updraft to keep coming because it keeps the updraft almost vertical. It prevents the inflow of downdraft of cold air from blocking that inflow of warm, moist air. So all of this keeps a very strong thunderstorm developed. Those are the ones that we look at to become severe. They may be in clusters, they may be in a line, they may even be a supercell. It all depends on how much instability and how much wind shear. If there's no wind shear, you can get a very strong thunderstorm. Probably not going to be severe. More likely it's going to have a lot of rain with it. So we know the Midwest is a haven for severe tornadic weather. There's a question in critical thinking that may show up this week of what's the synoptic weather pattern that favors severe thunderstorm development. Well, what did I just say? We need wind shear. Well, look at wind shear here in the Midwest. I have a high-level jet dipping down into the west of the area so that the airflow at that level is southwesterly. I have a low-level jet coming up out of the Gulf of Mexico that's southerly. See the wind shear? Now I want moisture. Well, there I got moisture coming in, maritime tropical air coming up from the Gulf of Mexico. I want lift. I have a strong cold front coming in from the west. All that combines to generate very strong, potentially tornadic thunderstorms. This is the classic setup for that kind of a situation. And it can't just happen out in the Midwest. You may get it in Ohio. You may get it in the southeastern United States. All those areas are possible. How does lightning form? Lightning is just the atmosphere. And interestingly, graupel, which is kind of a partially melted ice crystal, changes charge depending on its temperature. And that always struck me as very strange, and I do not claim to understand the physics behind that. But as graupel's temperature changes, it goes from being negatively charged to positively charged. And ice crystals do the same. So that means where these graupel and ice crystals are being put in a cloud, there's an opposite charge going on. And with that, you can see it here depicted. You have more of negatives heading down to the ground, which induces a positive charge on the ground. The lightning strokes come to the ground, and eventually, maybe the final step is all this positive charge coming down to the ground, at least temporarily, eliminating. And lightning can spread out for a long way from a thunderstorm. There have been reports 20 miles from the center of a thunderstorm where lightning hitting the ground, particularly out of anvils. So if you're outside, remember that you're much further away than you would actually expect. Downdrafts, while they don't cause as much know where they are generally. There are actually Doppler radars at a number of airports that look particularly for these little tiny microbursts that are very small. However, they can change winds by upwards of 170 miles per hour, depending on how the jet is flying. So if you think about it, when winds blow across the surface like a glider or whatever, it makes the plane lift, or an airplane as well. Then where they're going a little less, behind it, all of a sudden, well, the plane doesn't have that kind of lift, so it's going to go downwards. That is why it's a major problem, particularly on landing for aircraft or takeoff. Bow echoes or derechos. Derechos must be at least 240 miles long, with wind gusts over 58 miles per hour. And they're a type of a mesosail convective system. We talked about cluster of thunderstorms. That's it. Typically track from northwest to southeast. And you can actually see what they look like here. That an ordinary thunderstorm begins to develop. New ones form along it, creating a bigger and bigger bow. And you can actually get some tornadoes in these. Not often, but they do occur. And here's the hail. So we know that 1 inch is severe. Well, that means it's got to be at least quarter size. Anything less than quarter size is not considered severe. Can do some damage, but not severe damage. And yes, there have been softball size or greater diameter hail. And hail will form in the upper part of the cloud. Moisture gets up there. It keeps going up and down between the downdraft and the updraft until it gradually gets so big it can't be held up there anymore by that strong updraft and comes down and descends to the ground. Tornadoes are just very, very violently rotating. A circulation develops mainly in supercell thunderstorms. And because of that circulation, it starts in the mid-levels, usually tornado vortex signatures, and gradually descends. There are two main areas that we get thunderstorms. They're called Tornado Alley and Dixie Alley. One's Midwest, one's Southeast. Either way, typically, we have 1,300 tornadoes per year in the U.S. Nowhere else in the world gets anywhere close to that. Believe it or not, Pakistan is the next biggest area, and one area in Africa, and I think both are under 100. So we are way, way, way beyond anybody else in that area. And here you can see per 10,000 square miles. I like to do it this way rather than number per state, because you think about the number per state. States are bigger, they change size. This normalizes everything. You can see Kansas gets the most, Florida, Oklahoma, Illinois, all those areas. Even up in Ohio gets 5 for every 10,000 square miles over that time. This is a classic severe thunderstorm. It caused a lot of issues with the National Weather Service and how we do warnings. So what happened was a tornado developed to the southwest of Joplin, Missouri. We had a very good idea that the tornado in the Weather Service were going to develop. Warnings were issued all the way out to where 249 is on this map. They issued tornado warnings. And these were going to be over in the next hour. This is a long-lived tornado on the ground. The tornado developed and it moved east along that track. The eastern part of Joplin did not see that tornado until 45 to 50 minutes after that warning was issued. People did no longer believe there was going to be a tornado. They went outside, and some of those people died because of that. It made a really interesting sociology question as to, how long is an effective tornado warning? Even if statements are issued tracking this tornado, which we may not be able to do perfectly, people will still say, we've had this for a long time, this warning. It's not going to occur. And yet it may be because we had the ability to forecast it that far ahead, we may be able to give you that much time to really prepare. It's an interesting question. And here is the enhanced Fujita scale. Ted Fujita was a famous researcher at the University of Chicago who studied tornadoes. He's an interesting man. And he developed a scale that became called the Fujita scale. We enhanced that scale. Why? Because we wanted to relate it to damage. When you look at damage and you bring in civil engineers, they can estimate the wind speeds from the damage. So now, when we go out and do a survey on a tornado, the survey is strictly based on damage estimates. We look at what kind of damage occurred, how much of it, and all, and then relate it to the wind speed that must have happened to create that damage. And we have thousands of slides provided by civil engineers and all, and weather service people working together that relate this much damage to this much wind speed. So when we rate tornadoes, here for an example is a classic supercell thunderstorms and where the worst weather would typically be. You'll notice that south of the thunderstorm, that supercell thunderstorm, maybe some strong winds coming in, a rear flank downdraft might bring high winds. Then there'll be the tornado, then the large hail, small hail, and eventually the heavier rains in all north of that area. All right, there's a wall cloud. Why is there a wall cloud? Well, there's some rain that's going on, usually just outside this wall cloud. The wall cloud is tremendously rising air, so it grabs that rain-cooled air, pulls it into that strong updraft. When it does that, the air condenses and forms literally a wall cloud. It's a flat, circular cloud. Many times you can actually see them rotating. And what you can watch here, the beginnings of a tornado developed, and now it's beginning to dissipate. All through watching a wall cloud. And here's what it looks like on radar. Again, we have Doppler radar here to show the wind's direction, but we also can see the hook echo. So, try something here. Don't know how this is all going to work, but there's some very heavy rains occurring over parts of my area. So I thought I would try to give you a look relating what we just learned about this. And again, my computers are not the fastest, but all right, so what we have here, we have a line of showers and all across southeastern Virginia. Weak low pressure. There's a kind of a cold, warm front, stationary front across the southern part. You can see how the southerly winds are there. They kind of turn to northeast, almost east there, then northwest here. So there's kind of like a little circulation there. So I look at the morning sound. I wanted to look at that because this is a sounding for Waller, Virginia. Very, very moist. Tremendous amount of moisture. There's a little bit of dry air up here, around 850 millibars or so, but not a lot. So, and you'll notice the winds out of the east, southeast here, and from the southwest here. This is a little bit of wind shear, not real strong, but tremendous amount of moisture. So if you lifted the parcel here and follow the moist adiabat, which are these curved lines, I'm going all the way up, right up into here somewhere. But that is going to be giving a pretty good, healthy rise to the air. Pretty strong thunderstorm. And all that moisture, this is moisture convergence. So what's moisture? Well, we can have air converging, right? So why not have moisture? It's just a combination of air converging and moisture dew points. And you can see sea breeze developing down here and up right across my area where that front is. The air is converging with plenty of moisture coming up into it. And guess what? Where moisture convergence occurs, most thunderstorms develop. Finally, I wanted to show you a couple more things here. This is surface-based convective available potential energy. So how much energy is available for that lift? The bigger the number, the stronger the lift. Summertime gets pretty high. A lot of times we get over 2,000 Cape. Well, 1,000, 1,500, 2,000, 2,500 to 3,000 right there. Guess what? I am right in here. So I have about 3,000 of CAPE. That is pretty high. So you would think that there'll be thunderstorms develop. You can see them already out just to the west of this area. They have a lot of energy to work with right in here. This next one should be the amount of moisture available. Look at the water, the higher precipitable water. Summertime, you get precipitable waters above an inch relatively frequently. You don't get above 2 inches that often. Well, I have about 2¼ inches in this area right here. So that is a lot of moisture available to this thunderstorm. Like I say, there's some small, tiny potential for severe weather, but the main potential sure looks like it's going to be very, very heavy rainfall. And finally, I just wanted to see if I can get this. I don't know if this is going to work or not. But if I were to do a loop in this area right now of satellite, and we'll see if it comes up here in a second or not. But there's some clearing just south of that front or right along the edge of it. And with that, convection is going to fire later today. Here, I say, but that's what I look for. Those kind of things are what's used to forecast thunderstorms. Severity of them, how much it's going to rain or whatever. So since this is taking too long, I won't worry about keeping you on here. But that's what I wanted to just show you. You've seen how thunderstorms work. And here is a classic example of a bunch of thunderstorms today. So